Good morning, good afternoon, or good evening. In this video, we're going to be checking out section 1-4, continuity and one-sided limits in the good old calc book. In this section, we're going to determine continuity at a point and continuity over an open interval. We will determine one-sided limits and continuity on a closed interval. I've already talked about those one-sided limits in the last section. We will use the properties of continuity and then understand and use the intermediate value theorem, the IVT. So the book says, in math, the term continuous has much the same meaning as it has in everyday usage. Informally, to say that a function f is continuous at some point, x is c, means there's no interruption in the graph of the function at that point. That is, the graph is unbroken at point C, and there are no holes, jumps, or gaps in the graph. The figure below identifies three values of x at which the graph of f is not continuous. At all other points on the interval, from A to B, the graph is uninterrupted and continuous. And just think about it. If you can draw it without lifting your pencil off the paper, it's a continuous function. So if we look at these three graphs, all of them go from left x value A to B, A to B, A to B, A to B. And we see here as the function's coming along at point C, we have a hole in the graph. And then the function continues along on the other side of the hole. Of course, that is a discontinuity. We got a hole in the graph. Here, a little more extreme, we've got this open gap in the graph. The function is defined up here, and then there's a huge gap, and then the function picks back up. So that obviously is not a continuous function. Let me note again here in the first one too, this at point C was undefined. If we went up and looked, there was a hole in the graph and we'd go through it and float off into space. C is a little different here because the function is defined. It has this point defined down here, but other than that, there is a hole in the graph. So it is going to be a hole in the graph. That means it's not continuous. So we have a three-point definition of continuity. This you might really want to know for an upcoming test or quiz. It's also, this can be tested on the AP exam. So it says a function f is continuous at point 3 when these three conditions are met. 1, f of c is defined. 2, the limit as we approach c of our function exists. And then finally, the limit from part 2 is equal to the function value from part 1. Now, I've heard people explain this and say, it's 3 that is the important one because 3 assumes 1 and 2 have already happened. The function is defined and the limit does in fact exist. But again, for that AP test, you're going to want to know these 3 points. And I really think of these graphically. When part 1, it says the function is defined. Let me draw a quick XY axis here. Here's point C. It says the function is defined. That means we have a dot somewhere. We are going to run into the dot. The function is defined. Part 2, I'm going to switch over to red ink. It says the limit as we approach C of our function exists. Remember, that means the limit coming in from the left has to be the same as the limit coming in from the right. So this limit exists. We have a hole in the graph. So part 1 again is the dot. Part 2 is the line, the graph with the hole in it. Part 3 is what brings them together. Part 3 says that limit, the height of the hole, is exactly equal to the function. If you look at my graph right now, it is obviously not continuous. We have a hole in it. But if I give the part 3 where the function limit is equal to the function value, that means that the dot goes in the hole. So now the function's continuous. 3-part definition. We're defined, the limit exists, and here it says the dot plugs up the hole, and that makes our function continuous. A function is continuous on an open interval from A to B. Remember, the open means we're going to have parenthesis there, not brackets, when the function is continuous at each point inside the interval. A function that is continuous on the entire real number line from negative to positive infinity is called everywhere continuous. So now the book says, consider an open interval I that contains a real number c. If function f is defined on that interval, except maybe at point c itself, and f is not continuous at c, then f is said to have a discontinuity at that point c. Discontinuities can fall into 2 categories. They're either removable or non-removable. A discontinuity at C is called removable when our function can be made continuous by appropriately defining or redefining our function. For instance, the function shown, I'll bring this up here. The function shown have removable discontinuities at point C. Let me bring these up here. Oop. Oh, okay, here we go. We have a removable discontinuity. It's just a little hole in the graph. That's not much to get worried about. We can pave over that pothole possibly. This would be a non-removable discontinuity. When you have a big jump like that, no amount of algebra is going to save that function. Blah, blah, blah. Okay. Example 1, continuity of a function. Here the directions are they just say discuss the continuity of the function. So it might be easier to say where the function is not going to be continuous. And let's even figure out if it's going to be removable or not. So here, part A, this one. So we look at our function 1 over x. What number is going to mess us up? 0. We never want to divide by 0, so if we set that denominator to 0, x equals 0 is a discontinuity. So our domain, or we could even write, our domain of that function. We could write the set of all x such that x does not equal 0. Any other number is fine. We put a 0 in there. We're playing with fire, dividing by 0. So we have a discontinuity going on there. In this case, it's going to be non-removable. Usually, if you can remove it, it's done algebraically. In this case, we can't factor or cancel anything like that. So we have a non-removable discontinuity at 0. Now, if we look at B, x squared minus 1 over x minus 1. If we set that denominator equal to 0, if we set x minus 1 equal to 0, we get x equals 1. That is a discontinuity. So when our denominator zeroes out, we know we have a discontinuity there. We got to tread carefully. Can we remove this 1 or not, though? Look at the numerator, x squared minus 1. We could factor that into x plus 1 times x minus 1. X minus 1 is our denominator. Again, here, if we set our denominator equal to 0, we found this discontinuity. But when we factor and cancel, we figured out that this discontinuity is removable. When we factored and canceled, we paved over the pothole. Now, letter C is a piecewise function. When you see a discussion of continuity on a piecewise, first we can establish each piece is continuous. X plus 1, that's just a straight line, that's continuous everywhere. E to the x is our basic exponential curve. That is also continuous everywhere. So we know each piece is continuous, so our concern is going to lie at this x value. If we were going to start to graph these, we want to make sure there's not a gap when we make the transition from one piece of the function to the other. So if we're less than or equal to 0, we're on this line x plus 1. So we would have a y-intercept. Let me switch to a different ink. Here's our y-intercept of 1, and our slope is positive 1. So the graph is going like this, up approaching that point. Now, e to the x, if we are greater than 0. Well, what if we put 0 in there? E to the 0 would be 1, because anything to the 0 power is 1. So I'm going to use red ink here. The e to the x graph's first dot would fall right onto this graph's last dot. So here, I can draw this without lifting my pencil off the paper. If I switch over to blue ink, I'll start down here on the line. And as I'm going up, I can transition from the line graph to the exponential graph, and there was no gap there. So this one has no discontinuity. Each piece is continuous, and the piecewise function, put them together, is also continuous. Now, just for the sake of argument, let me go back here. I'll leave my x plus 1 graph alone. But if this other function was e to the x plus 3. So if we go to the x value of 0, we would have e to the 0, which is 1, but then we would have the plus 3. That would take us up here to 4. So the e to the x graph would start up here. So if this was e to the x plus 3, then we would have a discontinuity at that point. Again, the big thing with step functions, you're concerned about this, where you're transitioning from one function to the other. Approach with caution. Oh, okay, these are just the graphs we did. Back to here. A was 1 over x. The graph of that's going to look like this in the first quadrant. We have this going on, and in the third quadrant, in the negatives, we have something similar. But here at the origin, on the y-axis, we have a vertical asymptote. That is a non-removable discontinuity at 0. B, remember we had a hole in the graph at 1, but this one we factored and canceled. So when we factored and canceled, we pave over that pothole. A little hole's nothing. A big gap like this is trouble. And here's the book's graph of their x plus 1 line and the e to the x graph. Ooh, did I miss one? Oh, I guess I did. D, sine x. So think back to all the fun we had in pre-calc. Sine x would start at the origin, and when we get out to 2 pi, and every 2 pi after that, we would have another cycle. So our sine graph is going to look something like this. That's pretty terrible, but you get the idea. It's continuous everywhere. That graph is just going to roll out to the left and the right forever. It's everywhere continuous. And the graphs, of course, the book's graph is better than mine. All right. Now this, I did introduce this in the last section a little early. I think it helps to the overall understanding. One-sided limits. To understand continuity on a closed interval, you first need to look at a different type of limit called a one-sided limit. For instance, the limit from the right, or the right-handed limit, means that x is approaching our c value from the numbers greater than c, on the right of it on the number line. And this is denoted, we already talked about this, that little x approaches c from the plus side. There's a little plus superscript. So we have a limit from our right. Similarly, the limit from the left, or the left-hand limit, means x is approaching c from values under c, from the left of c on the number line. And we change that superscript from a plus to a minus to denote we're coming in from the left. One-sided limits are useful in taking limits of functions involving radicals. For instance, if n is even, if we have a square root or a fourth root, then as we approach 0 from the right, it's going to equal 0. We could not approach 0 from the left. It would be impossible on that graph. All right. So let's see here. Example 2 is a good illustration of these one-sided limits. It says find the limit of f of x is the root of 4 minus x squared as x approaches negative 2 from the right. Let's even come up with the graph of this. Square root 4 minus x squared, or the root of some number minus x squared, is going to be a half a circle. If we take the square root of the number leading under the radical there, the square root of 4 is 2. So this is a half a circle of radius 2, and it will be in the first two quadrants. So we're approaching negative 2 from the right. So here's negative 2. We're approaching from the right. That means we're approaching down this part of the semicircle. Could we approach from the left? There's nothing over here. So we could not approach that point from the left because our function is not defined. So let's write this out. The limit as x approaches negative 2, from the right-hand side of our function 4 minus x squared. Well, that's going to equal, we could get it from the graph. What's the height when we hit the edge of that? 0. Or we could always just do a direct sub. Direct sub does work on one-sided limits. So if we plug the negative 2 in for x squared, negative 2 quantity squared is 4, 4 minus 4 is 0. That is the height of this dot on our y-axis. Now, I don't think the book does this, but I'm going to switch over to red ink, and let's approach 2 from the left, positive 2. The limit as x approaches positive 2 from the left side, from the numbers under 2, of our same function, 4 minus x squared. We could do direct sub again or look over to the graph. As we're coming in at 2 from the left, we're working our way down this part of the graph, and we're approaching that dot. That dot's height on the y-axis is 0. If we try to approach either of these from the other side, that limit does not exist. And I'm sure the book's graph will be a little better than mine. There it is. So as we approach -2 from the right, that limit is 0. One-sided limits can be used to investigate the behavior of step functions. One common type of step function is the greatest integer function, or I sometimes just call it the step of x. Remember, that's where you round it down. You always round down. For instance, like here, 2.5 is rounded down to 2. And be careful if you're on the negative side of the number line, it rounds you deeper negative. So here, -2.5 rounds down to -3. It's always rounding down. So I think, did I change this one in my notes? Yeah, I'm going to change this one. We're going to approach 2 from the left and the right. So first let's draw ours. Oh, do I have a step function here? No, let's draw it. Let's draw that. I did not put it in your notes. So here's my xy axes. And if we're just going to do this step of x, let me do, let's go out to 3. 1, 2, 3. Remember, for this one, we plug a 0 in there. We'll have a defined dot at 0, and we head over, and then we have an open circle here. Anything between 0 and 0.99999 is all rounded down to 0. And then here's 1 on the y-axis. Our next step would start here at 1, 1, and everything would be rounded down to 1 until we get to 2. Once we get to 2, we're up here on the next step, and then everything's rounded down to 2 until we get to 3. So again, we're going to alter what the book has. Instead of approaching 0, we're going to approach 2 from the left and the right. Let me move this out here. So I'll do blue ink here. The limit as x approaches 2 from the left of the step of x. So we're going to approach 2 from the left. Here's 2. We're approaching from the left side of 2. That means we're moving along this part of the function. And as we're approaching 2, we're approaching this hole. And that hole has a height of 1 on the y-axis. Let me switch over to red ink, and let's approach that same 2, but now from numbers above 2, a little bit above 2 of our step of x. So here we are back at 2, but now we're above 2, working our way toward 2. So that means we're up here, working our way this way, and we're approaching this point. That point is at a height of 2. So, these one-sided limits are very useful, especially on something like this for a step function. If I were to ask just what is the limit as x approaches 2, it would be does not exist. And remember the reason, we're approaching 2 different numbers. Limit from the left is 1, limit from the right is 2. The overall limit would DNE, fail to exist due to approaching 2 different numbers. Just some odd problems. I must have just stuck them in there as a warm-up. Okay, here we go. When the limit from the left is not equal to the limit from the right, the two-sided limit is a DNE, does not exist. The next theorem makes this more explicit. The proof of the theorem follows directly from the definition of a one-sided limit. So when does a limit exist? Let f be a function. Let c and capital L be real numbers. C is a number we're approaching on the x-axis. Capital L is a limit on the y-axis. The limit of f of x as x approaches c is equal to L if and only if the limit from the left is equal to L and the limit from the right is also equal to L. Again, think about this graphically. As the limit from the left is approaching this hole, which is at a height L on the y-axis, and as we come in from the right, we're also approaching that same hole. When it's the same from the left and the right, the limit exists. So this concept of a one-sided limit allows us to extend the definition of continuity to closed intervals. Basically, a function is continuous on a closed interval when the interior of the function is continuous and it exhibits one-sided continuity at the endpoints. The definition below formally states this. Definition of continuity on now a closed interval. So a function f is continuous on the closed interval. Notice the brackets now from a to b. When the function f is continuous on the open interval, everything in between the endpoints is continuous, and the limit as we approach a from the right is f of a, and the limit as we approach b from the left is f of b. The function f is continuous from the right at a and continuous from the left at b. See figure 130. Do I have? Oh, I could probably just make something up here. Okay, so again, sometimes these definitions can be a little wordy. So we want to be, here's our interval from A to B, left endpoint A, right endpoint at B. We want to make sure we are continuous on that whole interval. So what we want to do is make sure f is continuous on the open interval from a to b. So at least here from the open interval from a to b, maybe I could draw the function like this. So we are continuous in between a and b. But notice we have these holes on the end. Are those holes plugged in? That's what this theorem does. As we approach a from the right, so here we are approaching a from the right, we need that limit to equal f of a. So if a goes into the function, I'm going to put a blue dot to plug up that hole. So the limit as we approach is equal to f of a. The endpoint's been blocked off. And then the other part here, I'll switch to red ink. As we approach b from the right, here's b. We're going to approach that. Oh, excuse me, I got that backwards. B from the left, we're coming in from the left. So we're working our way along this part of the function. The limit as we approach that hole should be exactly equal to f of b. So if I put f of b up here, we're not continuous on the closed interval. But as soon as I use that to plug up that hole, we now are continuous from the left and the right. So again, just to recap, the function is the endpoint holes are plugged in and the function is continuous everywhere in between. That is the definition of continuity on a closed interval. Similar definitions can be made to cover continuity on intervals from, open endpoint A to closed endpoint B, and closed endpoint A to open endpoint B that are neither open nor closed or infinite. So let's see what we got going on here. Example 4. Discuss the continuity of this. If we're going to be discussing continuity, it might be a good idea to figure out what the domain of this is. We got to be careful. I see an even indexed radical. So we want to make sure our domain, what is under that radical, that's a terrible squared, is always greater than or equal to 0. I'm going to add x squared. So x squared must be less than or equal to 1. Take the square root. X is between plus and minus 1. So if I square root it, remember I get the plus minus, the negative will sort of jump over. X must be less than 1 and greater than negative 1. So the domain here, x is between negative 1 and positive 1. The function itself in between negative 1 and 1 is going to be continuous. So what we got to worry about here is our endpoint continuity. So we could write the limit as x approaches negative 1 from the right of our function. I'm just going to write f of x. We got to see what that is. And we also want to check out the limit as x approaches positive 1 from the left of our function. And the good thing here, remember we can always just do direct sub and see what happens. If I plug the negative 1 in for x and I square it, I get 1. 1 minus 1 is 0, and the root of 0 is 0. So we are continuous from the right. Continuous from the right. As we approach positive 1 from the left, it's going to look very similar. When we square positive 1, we still get a 1 in there, so that's the root of 1 minus 1, or the root of 0. The root of 0 is 0. So now we're also continuous from left. Continuous from the left. And I see something down here in the corner. Just a better picture of what the graph is. Again, it is going to be half a circle, radical number minus x squared. The square root of that lead term is our radius, so there's our function. And what we did at the end, the direct sub, we did not know if these were open or closed circles. So we direct subbed in the one and the negative one and figured out the actual values so we could plug up those holes, and everything was fine. Now this, we're not going to fill in these values here, but where would one of these actually be used in the real world? Well, here's a neat example from Charles's law and absolute zero, if you've discussed absolute zero in a chemistry class at all. So what do we got here? We can use a one-sided limit to determine the value of absolute zero on the Kelvin scale. So on the Kelvin scale, absolute zero is the temperature 0K. Although temperatures very close to this have been produced in labs, absolute zero has never been attained. In fact, evidence suggests absolute zero cannot ever be attained. So how did science determine that the 0K is the, quote, lower limit of the temperature of matter? What is absolute zero on the Celsius scale? So to solve this, the determination of absolute zero stems from the work of the French physicist Jacques Charles back in the 1800s. Charles discovered that the volume of gas at a constant pressure increases in a linear relationship with the temperature of the gas. So if you have a set volume of gas and you increase the temperature, the gas will expand and have greater volume. If you reduce the temperature, the gas will contract and take up less space. The table illustrates this relationship between volume and temperature. To generate the value in the table, they took 1 mole of hydrogen held at a constant pressure of 1 atmosphere. The volume V is approximated and measured in liters, as the temperature is measured in degrees Celsius. So here at 80 degrees, nice and warm, we're at 29 liters of volume. Temperature goes down, gas contracted. Reduce the temperature, gas contracted. Reduce the temperature more, the gas contracted. As we keep lowering the temperature, the gases will contract. The points represented by the table are shown over here in the figure. Moreover, by using the points in the table, we can determine that the temperature and the volume are related by this linear equation. So somebody crunched the numbers, they figured out the slope of that line, is there 2 decimals in there? 0.08213 t plus 22.4334. Solving for t, we get an equation for the volume of the gas. The temperature is equal to volume minus this, all divided by that decimal. So by reasoning that the volume of gas can approach zero, but can never equal zero or go below zero, we could not have negative volume. And think about it, the table saying as we drop the temperature, the gas gets smaller and smaller volume. Theoretically, we could scrunch that gas down to almost zero volume if we could get the temperature low enough. So the limit, as our volume approaches zero from the right, we could never approach from the left. There's no such thing as negative volume. They figured out this, negative 273.15. And the table below shows the temperature converted to the Fahrenheit scale. Okay, again, just a neat science application of a one-sided limit. Now, properties of continuity, very similar to the properties of limits. We have b as a real number, f and g are continuous functions at that point. Then the functions listed below will also be continuous. So here, scalar multiple. If f is a continuous function and I just multiply it by a number like 2 or 3, the resulting function will still be continuous. Like if I have x squared is a continuous function. If I just multiply it by a 3, it's still going to be continuous. Sum or difference. If I have one continuous function plus another continuous function, then the resulting sum or difference will also be continuous. Like again, if x squared is a continuous function and x is a continuous function, if I add them together, I'm going to have another continuous function. There we go. 3, product. If I have one continuous function, x squared, and I multiply it by another continuous function, x cubed, the resulting function would be x to the 5th. It would also be continuous. So multiplying, taking the product of 2 continuous functions, preserves continuity. And quotients, if I have one continuous function, like sine x, divided by another continuous function, like x squared, it will be continuous But you just got to be careful. You don't want your denominator to go to 0. As long as your denominator is non-zero, the function will still be continuous. So a list below summarizes the functions we've studied so far that are continuous at every point in their domain. Important qualifier, some functions will have vertical asymptotes in their domain, but in their domains or between the asymptotes, they will have continuity. So any polynomial, like our good old x squared plus 7x plus 3, any polynomial is going to be continuous. Any rational functions, p of x divided by q of x, as long as your denominator is non-zero, it's going to be continuous everywhere in its domain. Same thing with radicals. Now we talked about, the square root of x looks like this. It's not even in quadrants 2, 3, or 4, but in its domain, it is continuous. Trig functions, sine and cos, are easy. They're continuous everywhere. Tan, cotan, and the rest of them, they do have asymptotes, but in their domains, between the asymptotes, they are continuous. And all our fun exponential and logarithmics, a to the x, e to the x, natural log of x, they're also continuous in their domains. So by combining Theorem 1.1 with this list, we can conclude that a very wide variety of elementary functions are continuous at every point in their domains. So applying some of these properties of continuity, let's see what we got here. We have f of x is x plus e to the x. Well, f of x equals x, that's one continuous function, plus e to the x, that is another continuous function. And I think it was part 2 of that previous definition, or properties, sums or differences. So this would be part 2 by that theorem, part 2. The resulting theorem is continuous. Continuous function plus another continuous function is a continuous function. The next one here, f of x equals 3 times tan of x. Well, tan of x is continuous, so tan of x is a continuous function, and 3 times a continuous function is another continuous function. Again, the tangent graph will have some asymptotes, but in its domain, it will be continuous. The last one here, x squared plus 1 over cos x. The numerator is a continuous function. The denominator cos x is a continuous function. Continuous divided by continuous is a continuous functions. So it is continuous, again, where we will have some asymptotes where that denominator does equal 0, but it is continuous everywhere in its domain. So continuous divided by continuous is continuous, but we will have asymptotes when cos of x is equal to 0. So there will be some in there. This next theorem, which is a consequence of Theorem 1.5, allows us to determine the continuity of composite functions. So here we have the natural log function, like the natural log of x is continuous, and 3x is continuous, but what about if we compose them? Or we know here the root of something is continuous in its domain, and the x squared plus 1 under it is continuous, but if we compose them, is that also continuous? And this theorem says if g is a continuous at point C and function f is continuous at g of c, that function's output, then the composite function f of g of x will also be continuous at that point. So one continuous function composed with another continuous function will also be a continuous function. Now some of this might get a little confusing here in example 7. Part A is not bad. It says describes the intervals on which each of these is continuous. So tan of x, do we remember how to graph tan of x back from pre-calc? Remember tan x, here's our xy axes. We will have our first vertical asymptote at pi over 2. And our next vertical asymptote here at negative pi over 2, and then at 3 pi over 2. Remember, there's a 1 pi gap between two asymptotes. So this gap is 1 pi. This gap is also 1 pi. So we're going to have asymptotes every 1 pi. Positive pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, on to infinity, and also off to the left. So we could write this, I guess it'd be a little more concise in a set builder notation. The intervals on which we were continuous would be the set of all x such that x does not equal, what would that be, pi over 2, starting with the very first asymptote, plus or minus 1 pi times some integer n. So that would cover every asymptote because there's infinitely many of them. Is the function continuous? Well, just not at these x values, not where x is equal to pi over 2 plus or minus all whole number adds or subtracts of pi. Now letter B, we've got a piecewise here. We've got at 0, our function value is 0. And then we've got here the sine of 1 over x if we're not equal to 0. So I'm going to just take this into some chunks here. The inside function here, 1 over x. 1 over x is not continuous at 0. Not continuous at x equals 0. Now, again, that 1 over x is the inside function. The sine of something is continuous everywhere, is continuous for all real numbers. Therefore, I don't know if you've seen this before, if I use this in pre-calc. Advanced, you might see these 3 little dots in a triangle. That's a therefore. So 1 over x, the inside function, is not continuous. The outer function, sine of something, is continuous for all real. Therefore, the composite, the sine of 1 over x, is not continuous at 0. Is not continuous at 0. So that limit will not exist. Again, our inside function, 1 over x, not continuous. The outer function is continuous. So we could just look to this theorem. If we have a continuous within a continuous, then the composite will also be continuous. Here, our inner function is what messed it up. That 1 over x gave us some trouble. So the limit does not exist. Our function is not continuous. Now here's what might hurt the brain a little bit. If we look at part C, the only change now is this x. This x was not here on this one. So this is x times the sine of 1 over x. And we are defined just like the last one, 0 at x is 0. Ooh, and first, let me back up here for B for a minute. This might help in the overall understanding of this. If we go back to B and look at our intervals, for part B, we had one interval from negative infinity to 0, and that interval left off, and the next one picked up at 0 and went to infinity. Notice the parenthesis, 0 was not included in there. So, and we figured out that the limit as we approached 0 of sine of 1 over x does not exist. That's a DNE. And we know that f of 0 is equal to 0. So here, they're not the same. The limit should equal the function output. By that 3-part definition of continuity, the limit as we approach should equal this, and the function will be continuous. So here, we're definitely not continuous. The limit as we approach isn't there, but our function is defined. We're going to see something different here in part C. So part C. Let's think about it like this. Sine of something, sine of anything, is going to be a number between negative and positive 1. Think about the old sine graph. Our peaks and valleys went between 1 and negative 1. So sine of something is between 1 and negative 1, and we're going to multiply that by this x. So we could say x times the sine of 1 over x is sort of sandwiched in the middle. We know that this part, let me underline it in black, this part is going to be either 1 or negative 1, and that's going to be multiplied by x. So the biggest we could ever possibly be would be positive x. The smallest we could ever be would be negative x. So this function must live somewhere in between negative x and positive x. Well, if we set this as a limit, let's let x approach 0. So if we let x approach 0, this one on the left here becomes a 0 is less than or equal to x times the sine of 1 over x, which is less than or equal to, this also turns into a 0. So we can see a little squeeze theorem in there. So I could write, therefore, the limit as x approaches 0 of this function, I'm not going to rewrite it all, I think they called it h of x. Yeah, h of x. Therefore, the limit as we approach 0 of h of x is also equal to 0. So let's back up. Just like part B, part C had intervals from negative infinity to 0 and 0 to infinity. And, oh, I shouldn't have erased it back here. Let me get rid of just this part. Here we found out the limit as we approach 0 as 0. And they also told us this part, that h of 0 is 0. So here we've plugged up the hole. Remember in part B, this limit failed to exist, so continuity could not be there. Here now, continuity does exist. The limit existed, and it's equal to 0. The function at 0 is equal to 0, so we've plugged the hole up, and this function is continuous. This would be continuous for all real numbers. Just some graphs to go with that. For part A, it was tan x. We established where the asymptotes are, so there's that graph for that one. And our last, was there more graphs on that? Yeah. Now for the first one, when it was just sine of 1 over x and we had 0 on there, as we did the limit, as we approached from either side, we ran into oscillating behavior. So our limit failed to exist. Even though the function was defined there, we could not say the function was continuous because of the limit failing to exist. When we put that x onto the sine of 1 over x, that's what they call a dampening factor. So we've now squeezed that function in between this line here, y equals positive x, and here's y equals negative x. So that sort of corralled our sine function. So it can't live outside of that x. So here our function was bouncing back and forth as usual, but it was getting pinched. It was getting squeezed into the origin. And since our function was defined at the origin, that preserved our continuity. You know, that function would be continuous where part B was not. All right, and moving on, I believe this is our last topic, the intermediate value theorem, IVT. This coming up, Theorem 113, it's an important theorem concerning the behavior of functions that are continuous on a closed interval. So this function says if f is continuous on the closed interval from a to b, and f of a is not equal to f of b, and k is any number between f of a and f of b, then there is at least one number somewhere in that interval from a to b, call it point c. There's somewhere a point in there that f of c will equal k. Does that make perfect sense? Probably not, but let's draw a graph. Do I have, okay, here. So we've got a closed interval from a to b. I'm going to put a here. I'm going to put b here. And it says f of a is not equal to f of b. This is a key part here. So I'm just going to pick a point, call this my height here. So this will be f of a. Oop, why did I write x? F of a, and I'll switch over to blue ink. I'm going to put b way up here. So way up here is f of b. So again, rereading the theorem, going with our graph, we are a closed interval from a to b. The inputs are at different heights. F of a and f of b are not equal. And k is any number in between. So I'm going to go right about in the middle, and I'm going to call this k. So now, again, it says at the beginning here, our function is continuous. So if I draw this k sort of as a dotted line, the conceptual question I could ask would be, can you connect f of a and f of b without not ever crossing the dotted line? It's going to be impossible. If I try to go sneak up this way, I'm going to hit it before I can get to the blue dot. If I try to go under it, maybe sneak across here, no, I'm going to hit the dotted line. It's also going to cross anywhere in between. I have to cross that dotted line to get from the blue dot to the red dot. There is no way around it. And, because I'm drawing this as a continuous function, I'm going to hit that point at some place, and that's what we're calling point C. F of C is going to be equal to K. So again, just to recap the theorem, the important part is the setup. F must be continuous, we must be on a closed interval, and those endpoints are at different heights. K can be any number in between. And it says here there is at least one number, C, in there. There could be more than that. If I do it like this, maybe to get from red dot to blue dot, maybe we take this path. Maybe there's 1, 2, 3, 4, 5 spots in there that f of c will equal k, but this IVT theorem guarantees us at least one. Okay, let's see here. I might as well read through this. The IVT tells us there at least one number C exists, but it does not provide a method to find that point. Such theorems are called existence theorems. And by referring to a text on advanced calculus, we could find that a proof of this theorem is based on the property of real numbers called completeness. The IVT states that for a continuous function f, if x takes on all values in between a and b, then it must take on all values between f of a and f of b. Let me see here. Yeah, okay. Nope, I guess where did we go? Yeah, as we go between A and B, we're going to put all of these points, infinitely many of them, into the function. Because our function is complete, that means we will achieve every output value between f of A and f of B. So that means we're going to hit that value of k in there somewhere. Oops. And I don't know how much. Yeah, and here's, and what happens if we start breaking down some of the if parts of that theorem? I stated that f must be a continuous function for this to work. Well, here's the scenario that if we don't have a continuous function, we might not have that value. So here's our f of a and f of b, but if the function is not continuous, maybe the value that we want, that k value, goes right through that gap. And also here it says we might have more than one point. Again, here's their f of a and f of b, and their k value hits that curve 3 times. So we're guaranteed at least one. There could be many more. Now let's see, in this one, example 8, application of the IVT, it says use the IVT to show that this polynomial function has a 0 somewhere between 0 and 1. So let's see, I'm just going to copy the function here. F of x, that's x cubed plus 2x minus 1. And our interval is 0 to 1. 0 to 1. So first, to make sure we can apply this theorem, there it is. We must be continuous on a closed interval. Our endpoint values must be at different heights. So we are in a closed interval, they told us. The function itself is continuous. It's just a polynomial. Let's check our endpoints. F of 0, if I put in the left endpoint, 0 cubed plus 2 times 0 minus 1 is negative 1. And then if I put the 1 in there, f of positive 1, well, that's going to be 1 plus 2 is 3 minus 1 is 2. So we've got a negative number and we've got a positive number, and what lives in between positives and negatives? Zeros. And that's what they want us to find, a 0 somewhere on that interval. So if we think about this graphically, that might not work. It says here at 0, we're down here at negative 1, and at f of positive 1, we're up here at a height of 2. So it's sort of like when we were talking about the theorem, is it possible to connect the negative 1 dot and the 2 dot without crossing the x-axis? We have to cross it somewhere. So we're going to be guaranteed an intercept in between. So we've done all the work on here. I guess I could write out, let me this over. So we've established the function's continuous, the interval is closed, our left endpoint is negative, our right endpoint is positive. I could write out by the IVT, by the intermediate value theorem, let me get this out of the way, there exists a point C in our interval 0 to 1 such that f of c equals 0, such that f of c is equal to 0. Now, in this example, we can't find it. We could throw this in a TI-89. We could get the exact value, at least as a decimal, and figure out where that intercept is. But here we're just using the intermediate value theorem to say that such a point does in fact exist. We're sure of it. We might not be able to find it, but we know that it does exist. Here in the book, it also has numerical solution. We could do that on a TI-89 if you typed in the function into your Y editor, and then you have your X and Y columns. I got a few values written down here. If you put in -1, you get out a -4. If you put in a 0, you get out a -1. If you put in 1, out pops a 2. Put in a 2, out pops an 11. So again, the problem stipulated we're in the interval from 0 to 1. So this is our interval, 0 to 1. We're going to attain every Y value between -1 and +2. So 0 crosses in there somewhere. We're guaranteed to have a point that meets that description. And what's this? Oh yeah, this is just their numerical solution. So we can see between 0 to 1, we're going to go somewhere. We're going to achieve all values between -1 and +2. Now what we could do also, because we know between 0 and 1 will give us an estimate, we could take the numbers between 0 and 1 and break it into tenths. Or here they did it by halves. 0, 0.5, and 1. And then they got these Y values. So we could keep, refining this estimate using our calculators if we wanted to. And I think in the homework, we will run into problems where we can actually find the number that would work. And if they ask you to find the value that satisfies the theorem, in this case, we would have just set this equal to 0 and found the x value that made it happen. Again, because this one won't factor nicely, it's not going to have a nice clean answer. We could use alternate methods to get there. And that's it for this lesson. I think I just have some odd problems here. Yeah. See you in the next video.